I previously made a video about creating programs for BitVM using logic gates. I'm happy to share that Super Testnet has built this 8-bit CPU for BitVM. He simulated this computer using logic gates, but now that we have this computer, it has some memory. It accepts commands written in assembly, so now anyone can create programs for BitVM using this low-level assembly language. You don't have to do logic gates anymore. So what I would like to do is walk through how this CPU works, and then go through a sample program, and then share a tool that I built that will help you write assembly programs. So if we go down here, we can see the supported commands. So to understand the architecture of the CPU, we have 16 bytes of RAM. That's memory, storage, and then we have register, and register A, where we are kind of actively doing computations. And so what we when we go through these commands, we're essentially interacting, either pulling stuff from memory to interact with the register, or we're putting the register back into memory. So if we look at this command number 1, LDA, we're loading a value from RAM into register A. So we're pulling from storage, putting it in there. Add, we're taking what's in register A and adding it to a value that's stored. We can subtract, again, same thing, register A, and subtracting a value that's stored in memory. And then STA, we are storing whatever we have in the active register to the memory, to a particular byte of memory. LDI, we can initialize a value. So instead of accessing memory, we're just initializing the register with a value. Jump, we can jump to another instruction. So I can have a few instructions laid out, and then a jump, and I can jump back. I create a loop, and I can go through some of those earlier instructions. JIC, this is jump if carry. I believe this is what it stands for. If I add numbers together and I overflow, if I go above 255, this carry flag gets triggered. It says that I need to carry a bit over. So this command, what it does is it adds a little logic. This is an if statement. If that flag is triggered, then we'll jump to whatever command we indicate here. Next we have halt. So I can create a loop that runs forever, or I could, if I have somewhere in my program this halt function, it'll stop any more computation. These next two .org and .word are for initializing, before the program runs, initializing a value in a particular byte of RAM. And then labels, I don't know, I guess you can write a function and label it, and then you don't have to rewrite that function every time. So that's kind of cool. I haven't played with that yet. So let's see how these things work in action. We'll go down to this sample program. There are a few here, but we'll look at this first one, count forever. In the assembly code, here we are initializing the register with the value 0. We're going to add to the register whatever value we have stored in byte 15, and then we're going to store the result in byte 14. And then we jump back to 1. So these slots in RAM are, the numbering starts at 0, so we're not jumping back to the very first command, we're jumping to the second one. So this is the command in slot 1. So we're going to jump back here, we're going to add what's in the register to what we have stored in byte 15, and then we're going to store the result again in byte 14. And then we jump back, and so we're continuing to add a number and then store the result somewhere else. And then here at the bottom, this is us initializing the value. So we are looking at byte 15, and we're initializing that with the value of 3. So if we go back to this program, we can see that every time it says add 15, we're adding the value 3 to whatever we have in the register, because we have 3 stored in byte 15. Kind of confusing to think about, so let's see it in action. So on this site we have the CPU in action here, so we can see every step it goes through and how it changes the RAM, how it changes its memory here. STU is the Super Testnet unit. That's what we're calling this thing. So we've got some sample programs. The counting one is the one we're going to look at. There's another bounded loop where it loops a few times and then stops. And then we have this use your own. You can, if you write a program, you can copy over the binary file for the program and then load it up here. We will do that in a second, but let's start with the counting program. So we've initialized things here. The way it looks, just to walk you through this, the first 4 bits are the command. So this is initialize in register A the value 0. That's the second 4 bits. Here we are adding, this is add whatever we have in byte 15. This is store whatever we have in the register into byte 14. And then this is jump. This is jump back to command 1, back to slot 1. So again, not slot 0, but slot 1. We walk through this. And then there's a lot of empty space here. And then we have in byte 15, in the very last byte, we have the value 3 is initialized. So I'm going to toggle this to decimal. This is, again, you know, the decimal representation of those binary bytes. This is helpful because we can now see how we're going to add 3 every time. So I'm going to walk through so you can increment the clock one step at a time. You know, I'm initializing 0. Great. I am adding what I have in 15. So I have 0 in register A. I'm going to add what I have in 15, which is 3. Now I have 3 in register A. And then next I'm going to store it in byte 14. So that's right here. We can see, again, click through it. Now we have 3 stored there. Then we jump back to command 1, back to slot 1. Great. Now we see add 15. So again, we're going to add that. We have 6 now in register A. Then we store it in byte 14, and so on. And we just keep doing that forever. So I'm going to auto increment the clock. You can see this run just forever now. It will continue to add 3, and we'll just continue to you know, see that number go up here in byte 14. So there's no halt command. This jump will keep this loop running forever. We don't have to watch it run forever. I'm going to stop the clock. But yeah, so this is how it works, and I would like to show you the tool I've made now, and we can write our own program. So this tool I've made, there's some instructions here, some links. So if you start here, you can link back to the other 2 pages we've been playing with. We have these are supposed to represent the initial RAM. So I have obviously commands here, and then whenever I change something here, you can see that it automatically changes the binary array that we have here. And so this is great. I like that, you know, I can just change this as it is and then copy this over directly. It makes the process a little bit easier when you're trying something new and you're making a lot of little changes. I can just keep jumping back and forth. So anyway, what I would like to do is I want to write a program that computes the Fibonacci sequence. And so the Fibonacci sequence, you have, you know, you start with 2 1s, and then you continue, you always add the 2 numbers together to get the next number in the sequence. So the next number is the sum of the 2 previous numbers. So what we are going to do here, sorry, quick note here, I'm not using .org and .word. I'm just using the command NOP. This is no operation. And then you can just initialize. So this is slot 14. Instead of using .org and .word, I could just put 100 here, and I've initialized this byte of RAM with 100. Anyway, it just made things simpler. That way I can have every byte of RAM here that you can play with. And anyway, so a note here that's different than the way Super Testnet was writing his programs. So anyway, what I want to do is I'm going to initialize these two slots as 1, and then I'm going to add them together in a way and store them here that these should alternate and continue to show the next numbers in the Fibonacci sequence. So think through this with me. What I want to do in the program is I want to load to the register what I have in slot 14, and then I want to add what I have in slot 15, and then I want to put it back in, I want to store it back into slot 14. I want to store the results so that I can compute bigger numbers. And then I want to do the opposite as well. I want to load what I have in 15. I want to add whatever number I have in 14 and then store it again in slot 15. And I want to just alternate that. So thinking this through, I'm going to load to register A what I have in 14, in byte 14. I'm going to add that to byte 15, and then I'm going to store the result back into byte 14. And then I'm going to do the same thing in the reverse order. Or with the opposite bytes, I'm going to load byte 15, I'm going to add byte 14, and then I'm going to store that back into byte 15. And now I want this to run forever, so I will put a jump here, and I want to jump back to the first command, which again is 0. So I've labeled the slots here. This should hopefully help you out. So I want to go back to the command that I have in byte 0, which is here. So I'm going to jump to 0. And so this should just continue to run. Let's see how it works. So I'm going to just grab this, make sure you get the brackets here. So I'll grab that, copy and paste it over here, and then I will submit it. So we have, again, if you want to look at the binary, I've got, load whatever I have in byte 14, add 15, store it in 14, so on. Right, this is what I have, and then in bytes 14 and 15 I've initialized 1 in both slots, and so let's toggle it back here and see how this works. So I'm just going to auto increment it. So we loaded, we added, we're storing. 2 is the next number in the Fibonacci sequence, then 3, then we've got 5, then 8 is going to be next, and so you can see the way that this is kind of alternating. It's loading it, adding, storing, loading, adding, storing, back and forth. This is going to run forever. Again, I've got this jump command here, so there's no halt anywhere. So you'll see at a certain point this carry flag will get triggered once we exceed. So these won't be true Fibonacci numbers in a second here. So 233, we're good there. But then now we've triggered the carry flag. We've exceeded what this computer can do. So I could fix it. I could add something to make it halt after a certain number of trials, things like that. I do want to leave you with a thought experiment here. There is actually a way I could simplify this. I can use fewer commands. Let me know in the comments if you figure out what that is, to achieve the same effect but with fewer commands. But yeah, hopefully this was helpful. Hopefully you are feeling inspired to try things out, see what you can build, see what functions, what programs you can write using assembly. I'll have all of these linked in the description, this tool and then the other 2 pages we were looking at. If you build anything interesting, feel free to leave it in a comment here, or let us know in the Telegram chat, which I'll also link in the description for BitVM builders. Join it, let us know how you're doing. Let us know if you've built anything interesting. So I'm excited to build out this BitVM, this virtual machine in Bitcoin, and hopefully we can continue to make it easier to access. So good luck.